I've seen a number of very interesting ways to propose on YouTube. One of the most fascinating to me recently was a young fellow who proposed to his girlfriend using binary notation. That is, just reciting a series of zeros and ones. And I'll create a link to that particular video in the description below mine. What I propose to do in this video is to create yet another nerdy way of proposing, and that is to graph with one equation, will you marry me? And I'd like you to come on a journey with me and see how to construct the whole thing. Welcome to Crystal Clear Mathematics, where it is easier than you think. I'm your host, Graham Henderson. This particular equation that we're going to build is composed of 55 separate elements. Now each element or part looks like a little straight line, but in fact it's an ellipse. Every component is based originally on the equation for a circle. So let's start there and in 3 steps see how to build the equation. The basic equation for a circle looks like that. It looks like Pythagoras' theorem, where x and y are the x and y value at any position on the circle, and r is the radius of the circle. And you can see that if that's the x distance to the point, and this is the y distance to the point, that x squared plus y squared equals r squared, because we have a right angled triangle. That means, for example, that x squared plus y squared equals 1 squared, or 1, is a circle with a radius of 1. And it would go through 1 and minus 1 on the y-axis, and 1 and minus 1 on the x-axis. Now, we can see that fairly clearly if we talk about the intercepts. And to do that, we replace x with 0 or y with 0. If we replace x with 0, you know that 0 squared is 0. Happens to be my favourite times table. But if we replace that with 0, we get y squared equals 1. And the solution to that is that y can be plus 1, because 1 times 1 is 1, or it could be minus 1, because minus 1 times minus 1 is also plus 1. Two minuses multiplied, two negative numbers multiplied make a positive. In the same way, if y is 0, we get x squared equals 1, and the solution to that is that x can be plus 1 or minus 1 when the y value is 0. So there we have a very simple circle. Now, if we wish to distort the circle so that we can squash it in or squash it vertically to make it elongated, what do? It turns out to be a very, very simple process. We simply divide the x squared or y squared by some other number, preferably a square. Let's see what effect that has. If y is worth 0, then y squared is 0, and it doesn't matter what's on the bottom. 0 over any denominator is 0. So x squared is 1, and the solution is that x is plus or minus 1. However, if x is worth 0, we now have this equation. If we multiply both sides by 3 squared, which happens to be 9, and solve this equation, we find that y can be plus 3 or minus 3, no longer 1. That means it can go down as far as minus 3 on the y-axis, or up as high as plus 3. Now I obviously didn't plan this well because it's going to go off the top of my board here, but we end up with an ellipse. It still passes through plus 1 and minus 1 on the x-axis, as we discussed, but now goes through 3 and minus 3 on the y-axis. This is how we can compress and enlarge the dimensions of a circle. I wonder how we might make an ellipse very, very narrow and a precise length. Well, let's have a look at that next. Let's imagine that I want an ellipse so narrow that when I graph it, it looks like a straight line or an interval. We'll draw it on the graph first. Let's say we want it to go through 2 on the y-axis and minus 2. But to make it incredibly thin, we would like it to go through 1/1000th and minus 1/1000th on the x-axis. So if we drew this ellipse, obviously I'm not going to be able to do this, it would be long and thin and so incredibly narrow that to the naked eye it looks like an interval. What would that look like? Well, we start with our circle, and remember, to get it to go through plus and minus 2 on the y-axis, we divide by 2 squared. So that when we solve that equation, y could be plus 2 or minus 2. This means that when I solve this equation to find the x positions, I want x to be worth 1/1000th or minus 1/1000th. And that's what we need. Now that's not the simplest way to write this. I suggest that it's actually a little bit easier to use scientific notation, or at least index notation. 1000 is 10 times 10 times 10, which is 10 cubed. We can simplify that even further. 10 cubed squared is 10 to the 6, or 1,000,000. And I will spell it out. Instead of dividing by 1/millionth, you know that we can multiply by the reciprocal, 1,000,000 over 1. This is a pattern that we use in fractions. Instead of dividing by this fraction, we multiply by its reciprocal, and therefore, therefore we can write 1,000,000 x squared, and that does the same job as this. So, this equation produces that line. Now if I wanted a horizontal line, let's do that in a different colour. If I wanted a horizontal line to go from -1 to +1 on the x-axis, then I would start my equation x squared plus y squared equals 1. This time my x values go from +1 to -1. And I want my y values to go from +1/1000th to -1,000th, and we can achieve that by using the same technique we used with the x's before. So this equation gives that line. So now we have the basic tools to construct little line intervals on a graph, ready to construct our letters. Now for step number 2. It's all very well being able to draw on our axes a vertical line or even a horizontal line centered on the origin, but if that's all we could ever manage, we'd only end up with a cross and we wouldn't be able to construct letters at all. We must be able to move these lines around the coordinate plane. And how do we manage that? Well, let's write our basic equation. There it is, that's our ellipse that goes from +2 to -2 on the y-axis and from +1,000th to -1,000th on the x-axis. So that's our interval. What if I wanted it to move to -5 on the x-axis? All I need to do is to make this alteration. And you can see that when x is worth -5, this becomes worth 0, or its value is 0, and this portion behaves exactly as it did back over here, where y would have values of +2 and -2. And it turns out that when y is 0, at this position, x would move from +1,000th to -1,000th. So we've in fact moved the interval 5 spaces to the left just by making that slight alteration. Now, in a similar way, let's change this number to -2, and let's have a bit of fun and change that to +3. You can see the same basic structure of the equation. It's an x squared plus a y squared equation, but with these modifications, this now has a centre at x equals +2 and y equals -3. On the y-axis, it moves from +2 to -2. And on the x-axis, it moves from +1,000th to -1,000th. So we have a vertical line here. How would we get a horizontal line? Well, we would simply swap these two coefficients, and we would get something like 10 to the 6 here, and let's use the same number here. Let's change the position. I'll use a +2 and a -3 this time. The centre of this graph is at -2 +3. It's not well positioned there. -2 and +3. So that's the centre of this particular line interval, or a very thin ellipse. Notice this time on the y-axis it goes from +1,000th to -1,000th, so it's extraordinarily thin vertically. But along the x-axis it goes from +2 to -2 away from the origin, from the centre of its particular ellipse. So 1, 2, 1, 2. And we've now constructed that line. So we now have the skill to create these very thin ellipses that look like intervals and to move them anywhere on the graph that we wish. Now for step number 3. Again, it's all very well being able to move lines around the graph, but if we could only ever graph one of them, we can't construct letters. So how can we, with one equation, have separate little portions of line scattered all over the graph? That's a very interesting question. Let me discuss it with you this way. There's our very basic ellipse at the origin. If I rearrange this equation, by simply subtracting 1 from both sides, I now have an expression that is equal to 0. This is the same equation as that, with the same information, drawing exactly the same graph. Now, mathematicians love zero when it comes to constructing equations. That's why, I think for the last 4 or 5 videos, I've been talking about zeros. I'm going to write it out again. Sorry, -1. That's that equation. Let's construct another one. You can see that it's almost identical. It's certainly identical in structure. All I've done is I've changed the origin. So I've created another line in a different part of the graph. Let's set this equal to 0. What's actually happened here? I have two expressions multiplied together to make 0. Now, if I challenge you to think up any two numbers that multiply to make 0, it won't take you long to realise that one of them must be 0. It happens to be my favourite times table. 0 times anything is 0. So if I have an expression times an expression equals 0, then either that is 0 or that is 0. Now if this is 0, it creates this line. If this is 0, it creates that line. In fact, any point on this line will make this equation true because it will make that 0. Any point on this equation, on this ellipse, will make this part of the equation 0, which will make the whole expression 0. We can actually stack these multiple times in an equation, which is exactly what I've done. I have 55 of them. Each individual bit makes one little ellipse. If I graph this very, very quickly, I haven't left a lot of room, but let's see what it looks like. This one is at the origin. It goes from +2 to -2. And it's 1,000th wide. There it is. This one is at x equals +1 and y equals -3. There's the centre. It goes 2 units up and down from the centre, up the y-axis and down the y-axis. And you can see that it's 1,000th wide. So those two lines are described by that equation. That one equation graphs those two separate parts on the graph. Let's put that all together to see how we can construct our equation stating, "Will you marry me?" I think you'll enjoy it. So here we have the first of the expressions in my equation. If I graph this, and I'm going to draw a very long horizontal line with a x and y axis and the origin, this has a centre at -25. X equals -25. I'll just estimate down here. And at y equals 0. So there's the centre of this particular ellipse. Notice that's 4 equals 2 squared. So it goes from -2 to +2 on the y-axis, or up 2 and down 2, and down 2. So it creates a little line there, and it's 1,000th either side of the centre. So again, that's our very thin ellipse. That's the first term. Let's look at the second one. As you can see, it looks almost identical with the first one. But this one now goes through x equals -22. Not quite as far as 25. And you can see that it goes through y equals 0. And again, we have 2 squared on the bottom. So it goes up 2 units and down 2 units. and we have the same coefficient of x squared, which is 10 to the power 6, which means it's going to go 1/1000th either side of the centre of that particular ellipse. In a similar way, all the following terms start drawing vertical lines and then horizontal lines building up the letters. With the one exception of the last expression, which is in fact a small circle, and we'll look at that now and then put it all together. Now I think you can see that it has the structure of a circle. It's an x squared plus a y squared equals, if we took this over here, equals something squared. In fact, if I rewrote it, 1/100th is in fact 1/10 squared. Where's the centre of this circle? It's at x equals plus 25, so unlike these ones, it's up this end. At y equals minus 2. And it has a radius of 1/10, a very tiny radius, so it's to make a little circle. The reason this is last is that's the final dot on our question mark, which I think from memory I've drawn something like that. I've restricted myself to straight lines because creating curves is a little problematic, and we might discuss that in another video. But for the moment, that's the kind of structure that we have, and this is the last element in the entire equation. So let's put it all together, and I just want you to see it unfold on the screen and to see the complete equation. Now, as I've mentioned before, this is going to be provided in a PDF file that's downloadable. The link will be in the description below this video, or you can go across to my website and find it there. Now that you've seen the equation, it's probably good that I show you how the graph is constructed. So you should see that unfolding on your screen now. Here's my challenge, or at least I have 3 of them. The first is that if you like what you've seen, then please experiment with the ideas or the concepts that I've shared. You've seen 3 very good skills that can be used to build up quite complicated relationships on graphs. The first is how to take the equation for a circle and modify it to make ellipses, even very, very thin ones. The second is you've learned how to move graphs around the coordinate plane. And the third is you've learned how to put equations for graphs together into one large expression to build up quite a complicated picture. I encourage you to explore that. The second challenge is this. If you feel you understand the concepts well enough, then why not make up your own statements? Build up an equation that when you graph it, says something else on the graph. And thirdly, if you're just a little bit nerdy and wishing to propose to your boyfriend or girlfriend in a particularly unusual way, then by all means feel free to use this idea. If you do so, I would love to hear from you. I'd love to see the video. And if you could create a link back to this to show people where the idea originated, I would really appreciate that. This is Graham Henderson for Crystal Clear Mathematics, where it is easier than you think, and I hope you thought it was. Please like this video, please leave a comment and subscribe to my channel, and I look forward to seeing you in the next video. Thank you.